You know, the ground beneath our feet feels so solid, so permanent, right? But what happens when all of that certainty just gets shattered in a matter of seconds? Today, we're going to dive into the incredible and, yeah, sometimes terrifying power of earthquakes and the amazing science that helps us understand our shaking planet.
All right, here's how we're going to break it down. We'll kick things off with the basics. What exactly is an earthquake? Then, we'll put on our detective hats and pinpoint where a quake actually starts, learn how we measure its raw power, and decode the different kinds of shock waves it sends out. And finally, we'll connect all that science back to the real world to understand why these events can be so devastating.
So, first things first, let's get a real handle on the fundamentals. What is actually happening deep in the earth when the ground starts to move like that?
Yeah, forget anything slow and steady. The two words to remember here are sudden and violent. This isn't some gradual shift. It's an enormous, super fast release of energy. You've got these massive blocks of rock under the Earth's surface that just snap. And all that pent-up energy has to go somewhere, right? So it explodes outwards in the form of these incredibly powerful seismic waves. Okay, so where does a quake actually kick off? It's not just random. Every single earthquake has a precise point of origin, kind of like a ground zero, but deep, deep within the Earth.
So, way down in the Earth's crust, you'll find the starting point of every quake. It's called the focus. You can think of it as the underground ignition, the exact spot where the rock first breaks and unleashes those initial powerful shockwaves. Now, while the focus is where all the action starts, the epicenter is where we feel it the most. It's the spot on the surface that's sitting directly above the focus. This is the location you always hear about on the news, and for good reason. It's where the shockwaves hit the surface first and usually cause the most intense shaking.
So let's make this super simple. The focus is the hidden cause, way down underground. The epicenter is the effect we see and feel up on the surface, the place that gets hit the hardest. One is the source, the other is the headline.
So we know what a quake is and where it comes from. But that leads to a pretty huge question, doesn't it? How in the world do you measure a force that can literally move mountains?
Seriously, think about that. This question really gets to the core of the challenge for scientists. When the very ground you're standing on is shifting and breaking, how do you assign a number to that? Well, it takes some pretty incredible tools.
And the answer is this amazing instrument called a seismograph. It's so sensitive, it can record the tiniest motions of the ground. As the Earth trembles, this machine creates a dramatic visual record, that jagged line we've all seen, which is basically the earthquake's unique signature, capturing all its power and how long it lasted.
But all those jagged lines need to be translated into something that we can all understand. And that's where the famous Richter scale comes in. It was developed by Charles Richter to take all that raw data from the seismograph and convert it into a single number that tells us the quake's magnitude.
The scale gives us a quick way to classify quakes. You know, a 4 might just rattle your shelves a bit, but a 7 can bring down buildings. But here's the part you've got to remember. The scale is logarithmic. That means each whole number is 10 times more powerful than the one before it. So a magnitude 7 isn't just a little bit worse than a 6. It has 10 times the shaking amplitude. That's a mind-blowing difference in destructive energy.
Okay, so we've measured the quake, but what about the shaking itself? Well, it turns out that energy doesn't just travel in one simple way. Nope, there are actually different types of waves, and each one moves the ground in its own unique and pretty distinct way. The first big split is between body waves, which shoot right through the planet's interior, and surface waves, which, you guessed it, only travel along the surface. Now, the body waves are the speed demons. They arrive first, but it's usually the surface waves that are the most destructive.
Let's dive into those body waves. First up, we have P waves, and the P is for primary. They're the fastest, so they're the first to arrive. Imagine pushing and pulling a slinky. That's a P wave. Right behind them are the S waves, for secondary. These are nasty. They move the ground from side to side, kind of like cracking a whip. And that shearing motion is what does a ton of damage to building foundations.
And then, finally, the slower but often most destructive surface waves roll in. You have L waves, which create the snake-like side-to-side movement. But the most terrifying ones, those are the Rayleigh waves. They make the ground itself roll up and down, like you're on the surface of the ocean. This combined chaotic motion is what causes the most catastrophic damage to our buildings and roads. So we've got the science, the anatomy, the measurements, but what does all of this actually mean for us? This is where we connect the physics to the very real
and very profound consequences for people. Well, one of the most devastating effects happens when an earthquake's epicenter isn't on land, but on the ocean floor. That sudden vertical shift of the seafloor can displace a colossal amount of water, generating a series of incredibly powerful waves we call tsunamis. And these waves can travel across entire oceans to absolutely flood coastal areas.
And the impact on land is, of course, just as severe. A major earthquake doesn't just shake things up, it tears apart the very fabric of a community. It destroys our infrastructure, buildings, roads, bridges. It causes landslides. It can literally reshape the coastline. And after the shaking stops, the immediate disaster is followed by critical shortages of food, clean water, and medicine. And most tragically, the immense loss of life.
You know, understanding the focus, the shock waves, the Richter scale, it gives us the what and the how of an earthquake. And that knowledge is truly our first line of defense. But it all leads to the most important question of all. How do we take this science and turn it into action? How do we build stronger, more resilient communities that are prepared for what